Hey guys, today we're going to look how momentum conservation is changed slightly when we look at two-dimensional problems. Today we're only going to look at inelastic collisions, which are the collisions that the two objects stick together. So when two objects collide, we already know that their momentum is conserved. If they are traveling in different directions though, like north and east or south and west, their momentum is conserved in each individual direction that they are traveling. So the eastward momentum has to be conserved, and the northward momentum has to be conserved. This means that we will have to analyze the objects in the two separate directions, north only, east only. Or, depending upon the scenario, we could combine them using Pythagorean theorem, but that's going to depend upon which example we're looking at. Today, we're going to have one of each. So here's a picture of an inelastic collision. An object's moving from the east in this direction, and a second object's moving to the north in this direction. When they collide, they travel off in this direction. Now, I don't necessarily like how this picture is drawn because it is not drawn tip to tail. But you need to know that as a result, the momentum in each direction is combined to produce a final momentum. So if we draw this properly, we have the red arrow going this way, the green arrow going this way, and our blue arrow finishing off that triangle. So all I did was take these vectors from the picture and put them in tip-to-tail form. Now the reason why I leave the picture as it is and then draw tip-to-tail is because when we talk about collisions, most of you actually picture what is physically happening in the photograph. We will use the concept of vector addition or resolving vectors and Pythagorean theorem to solve for our unknown variables. So we are going to have three different ways that we're going to adjust our equations. Our first way, momentum is mass times velocity, we are going to plug in to Pythagorean theorem. But each individual value has to be a mass times velocity. We can't just do the mass, we can't just do the velocity. We need the product of those two values as A, B, and C. The second way that we can do this is if we have our first arrow and our second arrow and our hypotenuse, maybe we have our mass times our velocity here, but we're solving for an unknown on one of the legs. If we do that, we're actually going to take this blue arrow and we're going to separate it out into its two components of momentum. We're going to take that blue line and I'm going to solve for this leg or this leg because I have this whole blue line's value. And if I do that, I want to solve for the adjacent leg and the opposite leg. So I'm going to be using sine or cosine. And I'm going to have the momentum in the x direction is equal to the momentum times cosine theta, and that's the yellow line. So the momentum in the x direction is mass times velocity times cosine theta. The momentum in the y direction is going to be the same thing, but instead of cosine, we're going to use sine. So the mass times the velocity times sine theta. So we use these two if we want to solve for the yellow line or the green line in this bottom picture. So these are the three equations we're going to be looking at. We're going to be using Pythag again. We're possibly going to be using momentum times cosine theta and possibly be using momentum times sine theta. So for our first example problem, we're going to keep it easy and we're going to use Pythag. So you have two carts at an intersection collide and lock bumpers. Find the final velocity, both magnitude and direction of the cars. So we have the 500 kilogram car moving eastward. We have the 400 kilogram car moving northward. They hit and there's a big collision and then they travel off together at some direction this way. So again, I don't like this drawing, so I'm going to redraw it down here. It's my red arrow, my green arrow, and my blue arrow. I'm just taking those vectors and readjusting them. Now I have to do two things. I have to find the momentum of the red arrow, which is mass times velocity. So that's 500 times 2.5. and that is 1,250 kilograms times meters per second. I have to find the momentum of the green arrow, mass times velocity, so I have the red arrow, it's a value of 1250. I have the green arrow, it's a value of 600. I want to solve for the blue value, and I want to solve for this angle and direction. So in order to solve for that blue line, I'm going to use Pythagorean theorem. So I have a squared plus b squared equals c squared. 1250 squared plus 600 squared equals c squared. 1,562,500 plus 360,000 equals c squared. Add those up, and 1,922,500 equals c. If I square root that, I have a momentum of 1,386.54. So this blue line has a momentum of 1,386.54. But the problem is asking me for the final velocity, and this is the entire momentum. So I have to go back to a momentum equation, but because this is an inelastic collision, I'm going to take my masses and add them up and multiply by my velocity. So 1,386.54 equals 900 times v. Divide out that 900, and our velocity is 1.54 meters per second. So that's part of our answer. The other part of our answer is direction, and in order to find our direction, we have to use inverse tangent. So tan to the minus 1 of opposite, which is 600, over adjacent, which is 1250, and that equals theta. Tan to the minus 1 of 0.48 equals theta, and theta equals 25.6 degrees, blank of blank. The first arrow we drew was east, so that's the second blank mark, so north of east. I'm going to write the whole thing all over again at the top because I ran out of room. Our final velocity is 1.54 meters per second at 25.6 degrees north of east. So after our collision, those two cars stuck together and traveled in this direction with a velocity of 1.54 at an angle of 25.6 degrees north of east. Now our second example is going to be slightly different. Now we have all of the final information and the initial information for the northward object, but we do not have all the information for the eastward object. So two cars in an intersection collide and lock bumpers, find the initial velocity of the first car. So this arrow, this upward motion, I don't actually care about. So I'm just going to cross it out. I'm not going to use it. This vector over here is at an angle. We have the value of the hypotenuse. We have the angle with the horizontal. So what I can actually do is separate this vector out in the x component and the y component, because previously I stated that the momentum is conserved in each individual direction. So since my initial velocity is unknown here, the only direction I care about is the x direction. So I can solve for the value of that green line. Now, I could solve for the momentums of the eastward and the northward and the hypotenuse, so a squared plus b squared equals c squared. I have 500 times v squared plus 600 squared equals whatever this is squared. And when I distribute the squared symbol, I tend to make silly math mistakes. So I'm going to choose to avoid that by not using Pythag for this example. So instead of that, I can use the initial momentum in the x direction equals the final momentum in the x direction. And I have mass times velocity, and I need to find this value. So I know this has a value of 1080 because 500 and 400 added up is 900, and I have to multiply it by 1.2. So this line has a value of 1,080 kilograms times meters per second. I also know this angle. And if I want to solve for that green line, I am solving for the adjacent line, so I'm going to be using cosine. So I'm going to have mass times velocity times cosine theta. My mass of the object before the collision is 500. My mass after the collision is 900. My velocity after is 1.2. The angle that I'm moving is 35 degrees. (500V) equals 915.89. Now I want to divide by this 500, and my initial velocity is 1.83 meters per second. So that's all we had to do. And like I said, I skipped this step of possibly using Pythagorean theorem and just used the x direction of the momentums to save myself some possible math errors. Okay? So at this point, when I see you tomorrow, we're going to practice solving for unknowns using both of these scenarios, using either Pythag or using the x direction and the y direction only to solve for just one direction of the motion. So I'll see you tomorrow so we can do that.